Welcome everyone. In this video, I want to go over the solution of the sample final. Some problems we're going to see probably 5 or 6 of them, and then the next video I'll go over the solution of the rest. So let's just start going over these problems, and we'll see when we can stop. So number one, it says determine the singular point of the given differential equation. Classify its singular point as regular or irregular. So the first step to do that, what you need to do is to divide the equation by the coefficient of y double prime, which in this case is x squared times x minus 5 squared. So if you divide all the terms and then you do that to find out what P of X is and what Q of X is. That's a simple simplification. If you do that, P of X is 4 over X times X minus 5, and Q of X is X plus 5 divided by X squared. And of course, this is 0. So P of X is not defined at X equals to 0 and at x equals to or at x equals to 5. So 0 and 5 are singular points. Now let's test to see if they're regular or irregular. To do that, for x equals to 0, you multiply p of x by x and q of x by x squared. So again, take the factor, first multiply it by p of x and the factor squared times q of x. If you do that, then x p of x becomes 4 over x minus 5 squared, and that is defined at x equals to 0, and x squared q of x becomes x plus 5 over x minus 5, and that is also defined at x equals to 0. So therefore, you can say x p of x and x squared q of x are both defined at x equals to 0. Therefore, x equals to 0 is singular regular point. Now let's test for x equals to 5. So you take x minus 5 times p of x, and if you do that, you get 4 over x times x minus 5. And you know right away this is not defined at x equals to 5 because it can make the denominator 0, and you can stop right there. You don't have to check x minus 5 squared times q of x. If it doesn't work for one of them, then you can say therefore x equals to 5 is a singular irregular point. Number two, we want to solve this by using power series. So there's no singular point here. So if you want to solve it, you just say y equals to the sum n starting from 0 to infinity a sub n x to the power of n. Take the derivative of that using the simple power rule for derivatives. So it's going to be n times a sub n x to the power of n minus 1. And don't forget that starts from 1. And y double prime of x is n times a sub n times n minus 1 x to the power of n minus 2. And that starts at n equals to 2. So if you go ahead and substitute in the equation we have x squared plus 2 times y double prime. So times that, and I did that here, plus 3x times y prime. So times that, and I wrote that here, minus y, which is that equals to 0. Now if you distribute that to x squared and to 2, so the first term x squared times x to the power of n minus 2, just x to the power of n, and then 2 times that, we get 2n times n minus 1 times a sub n x to the power of n minus 2, and the 3x x times x to the power of n minus 1 is just x to the power of n, and this doesn't change. Then you test. If you put 2 here, you get x squared. If you put 2 here, you get x to the power of 0. If you put 1 here, you get x to the power of 1. And if you put 0, you get x to the power of 0. You take the highest exponent. That's what you have to bring the other ones to. So this term doesn't change. For this term, to make that an x squared, you have to substitute n by 2 and n by 3. So you need the first two terms, and for this one to make it x squared, so you need n equals to 1, and for this one again you need 0 and 1. And if you substitute all that, so that doesn't change. If you put 2, if you substitute n by 2, then you get that term, and if you substitute n by 3, you get that term, and plus, then the next term starts from 4 to infinity, and you write the same thing. This one just needs 1, so you get 3a1 times x, and then you start from 2 to infinity, and you write the same term. And finally, the last one here, but we needed it 0 and 1. So if you substitute, you get a0 plus a1 times x, and starting from 2 to infinity, a sub n x to the power of n. Now, if you simplify this more, so you can, this is just arithmetic. So here you get 4a2 x to the power of 0, 12, a3 times x, and the power series, they stay the same. And you can kind of simplify, rewrite the equation, and let's see what we can do now. We're going to take the terms with non-power, or we call the non-power series terms. So those, and we know they are equal to 0. There is no function here or forcing function here. So these, you put them equal to 0. Then you take the power series, the terms with power series, and you put that equal to 0 also. However, for number 2, for this one, what we want is all of them to have x to the power of n. So this one is n minus 2, so you add 2 to each n and subtract 2 from the index here. And if you do that, then you get all the terms with x to the power of n, and you can factor at that, and this is the coefficient, and you know that should be equal to 0. So now if you simplify this, you have terms with a sub n, and you have terms with a sub n plus 2. So you can separate them, and the factor of a sub n is n squared, the coefficient is n squared plus 2n minus 1, and the factor of a sub n plus 2 is 2 times n plus 2 times n plus 1. And again, times a sub n equals to 0, and n starts from 2. So these are integers. If you take the coefficient and put it equal to 0, then you can isolate a sub n plus 2, because what we want is a recurrence relation, and you get a relation between a sub n plus 2 and a sub n. And again, this is simple algebra, that's what you get. For the constant terms, if we go back here to number 1, so you take all the constants and put it equal to 0, and all the terms or coefficients with x and put them equal to 0. Please try to redo this yourself, and you'll see it's going to become very clear. The constant terms, you have 4a2 minus a0 equals to 0, and the terms with x are 12a3 a sub 3 plus 2a1 equals to 0. Isolate a sub 2, so you get 1 over 4 times a0 times a0, and a sub 3 is 1 over 6 times a1. Now, why did we do this? Here we're going to start, if n equals to 2, then you know that you can say a4 equals 2, and if you calculate that, you get negative 7 over 25 times a2. But a2 from here, we know it's 1 over 4 times a0. You substitute and you get that. N equals to 3, a5, you get that, and if you simplify, you get that times a3, that's negative 14 over 40. But what is a3? A3 is 1 over 6 times a1, so you get that one, and you can come back and write the solution. So the solution, the power series is y is a0 plus a1 plus a2x squared plus a3x cubed and so on. But we need all the terms to be in terms of a0 and a1. So you can write 5 terms, and a0 is what, a1 times x. Then you have a2, but what is a2 is 1 over 4 times a0. So from here you substitute, and the rest are exactly the same thing. So if you have a3, you know that a3 is negative 1 over 6 times a1x cubed, and you get an idea of the solution. Then you separate the terms with a1, a0 and the terms with a1. So this is going to be a0, and the terms with a0 have all even exponents, and the terms with a1, they all have odd exponents. So basically, this is our y1 and this is our y2. In the solution, we know it's written as c1 y1 plus c2 times y2, where a1 represents c1 and a2 represents c2. And if you want to write this for each one, 3 terms are good enough. So this is the solution. Number 3, use the method of Frobenius to find the initial roots of the singularity. So we do not need to solve this. So first of all, if you look at this equation, you know x equals to 0 is a singular point. So, or I said x is singular. Now, Frobenius method, instead of writing x a sub n x to the power of n, you can just start with that, and that's going to give you the solution very nicely. Why is that? Take the derivative, same thing, power rule, take the second derivative, and go ahead and substitute into the original equation. So this is a lot of algebra work, and simplify. So now our goal is, once you write all that, so but first of all, x squared times that is just x to the power of n plus r. So these are just like the last problem, x times x to the power of n plus r minus 1 is just x to the power of n plus r. And this one is you just distribute the power series to x squared and 1, and finally you get this expression. But what is our goal? Our goal is to take x to the power of r out. So this one, you can write that as x to the power of n times x to the power of r. This one, you can write that as x to the power of n plus 2 times x to the power of r. And these are same way as this one, and factor out x to the power of r. So the first one, you're left with this. Now we have all n's here, and you continue the same thing we did with the last problem. If you start with 0, you get x0, here you get x0, and here you get x to the second power. So this stays the same, and this one needs 0, 1 to bring that to squared, and this one also needs 0, 1 to bring the power of x to square. So we're going to get some non-power series term, and I did those separately here. So for number 1, first you substitute 0 and then you substitute 1, and you continue the power series with n starting from 2. For number 2, you put 0 and you put 1 and minus the power series, and you start from 2. Number 3 did not need to change because it was x squared. And number 4, again, if you do that, you get a0 x0 plus a1 times x plus, and that just starts from 2. Now the initial equation, what you want to do is take the non-power terms and then factor out x0, 0 for all the non-power terms. If you do that, that's what you get. And so that's x to the power of 0, and you have the ones with the coefficient of x's are 1. So you put all of them together, and from here you can factor out an a0, and from here you can factor out an a1. Now note the coefficient of the smallest power of x is the initial equation. The smaller power of x here is x0. So this is our initial equation. This is a quadratic equation. You can solve for r, and you get r equals to 1 or r equals to 1/2. All we needed are the initial roots. Now to finish this equation is pretty long. You have to do it with r equals to 1 first, and now r equals to 1/2. So basically, this is what you're going to have on the exam. Just go ahead and find the initial roots, and that should be good enough. Use the definition to find the Laplace transfer f of t equals to sine hyperbolic of kt. You may use exponential transformation. So now the Laplace transfer of this, so you know sine hyperbolic affects the exponential notation is e to the x minus e to the power of negative x divided by 2, and I put for the cosine hyperbolic also. We don't need this in this problem, but the way you write this, so you can say this is the same thing as 1/2 the Laplace transform of e to the kt minus e to the kt. And for this one, again, the Laplace transform, please check that is 1 over s minus k, and this one is minus 1 over s minus k. And if you simplify that, actually the 2 goes away because you get 2k and it simplifies with k, and that's what the answer is. No solving an equation, it's just the Laplace transform. Now let's see, this is the same type. If you have the Laplace transform of t to the power of n f of t, the way you write that is -1 to the power of n, and the nth derivative of the Laplace transform. So now you write your -1 to the n is 2 here, and you take the second derivative, and we know that the Laplace transform of sine hyperbolic of t is 1 over s squared minus 1. And to get that answer, what you need to do is to take the derivative of this function twice. It's the second derivative. Just use the quotient through a couple of times and check your answer. That should be the answer. I think that's good enough for this video. I'm going to stop right here, and in the next video, I'll go ahead and solve the rest. Thank you for watching, and I'll see you in my next video.